In our previous lecture, we talked about what a linear system is, and in this lecture we will talk about what a linear system is not. Okay? In other words, we'll talk about nonlinear systems and their relation to linear systems through the process called linearization. Okay. So let's visit one of the most famous nonlinear systems in town. Okay. That will give us an idea of how to represent a nonlinear system. Okay. Let's consider the inverted case. Okay. Inverted pendulum. Namely, we have some weightless rod and with a mass attached top, and there's a pivot here. It can move to right and left, and this is the direction of gravity, G, and this is the vertical line. Okay, so let's measure it in clockwise direction, and this angle is labeled theta. L is the length of the link, and let M be the mass of this ball, okay, attached to the fixed stiff rod. So the second order differential equation describing the dynamics can be derived as an L squared theta double dot, this is angular acceleration, equals NGL sine theta minus some positive constant times theta dot. This term represents friction, and suppose that we also have some input over the system, namely torque, where tau stands for torque, and we're going to consider that as our input to our system. And B is the friction coefficient. Okay. Now, this is perfectly valid representation of the system, but for analysis, usually it's better to put this into another form. So that what we already applied to our linear systems and obtain state space representation. Now let's do the same thing and obtain state space representation for this nonlinear system. For that, what we do is we have to choose our state variables. Okay, so this is a second order system because this is the highest order term that appears in our equation. So that means we have to choose two state variables. Okay, and together they make our state vector. For a physical system, it's usually best to go with the natural choice, namely position and velocity, or angle and angular velocity. Okay, so to obtain the state space representation, of inverted pendulum can be obtained by letting, for instance, the first state variable to be angle, the second state variable be angular velocity, theta dot, and input is already defined tau, but to make things fit to our notation, let's from now on represent tau with u. U is the letter that we use for our input. Okay, this is tau. Now in this case, what happens is, to obtain state space representation, what we do is we obtain x1 dot in terms of our state variables and input, we obtain x2 dot in terms of our state variables and input, and then put everything in vector form, and that's our state space representation. So what's x1 dot? x1 dot is theta dot, and theta dot is x2. Okay, so we have x1 dot x2. So we have expressed x1 dot in terms of our formulation variables. Okay, so that's what we want to do. Likewise, x2 dot equals theta double dot. And then theta double dot is this thing divided by NL squared. And what we have is sine of x1. And here, theta dot, which is x2, so everything, and this is our input, so everything will be in terms of our state and input. And if you organize the terms, this is what we have. G over L sine theta, which is our first state variable, minus B over ML squared theta dot, which is our second variable, x2. And finally, we have plus 1 over ML squared times tau, and tau is our input here. Okay. And let output for the system be, that is, suppose what we measure is this angle, okay, through some encoder, let's say, and let output be theta. Okay. Therefore, immediately we have output equals the first state variable, x. So what we have is x dot equals something in terms of formulation variables, and y equals also something in terms of our formulation variables. So what we do is we collect all those terms, put it into a single vector equation. That's our state space representation for our nonlinear system. Then we have x dot equals f of xu, and y equals g of x for functions f and g. And what are these functions f and g? They're sitting here, okay, where f of xu equals x2 is the first entry of this vector function, and the second entry is sitting here. So let me rewrite it. G over L sine x1 minus b over ml squared x2 plus 1 over ml squared. Okay. So basically what this function does, it takes three scalars, x1, x2, and u, and it generates a vector in R2. Okay? And that 2 in R2 is the order of our system. It's a second order system. So that's our f of xu, and g of x is simply x1, first state variable. Okay? Since the output is scalar, what this g does, it takes three scalars, x1, x2, and u, and in this case it doesn't depend on u, so it was okay to write just g of x, and it produces a scalar which we call the output. Okay, now what the generalization should be like is now obvious, so let's put that down, and then we will move on from that point. So, in general, the state space representation of a nonlinear system looks like the following. Representation of a nonlinear system. X dot equals f of xu, and y equals g of xu. Okay? In our case, we just had g of x because the input didn't directly, the output didn't directly depend on the input, but we could have written g of x and u. It wouldn't be wrong, okay, from the grammatic point of view. So this is the state space representation where f is a vector valued mapping, okay, from Rn times Rk to Rn. So this is the space that our state belongs to. X in this case, in our example, it was R2, but in general it would be Rn, and this n is the order of the system. This is the number of individual inputs that we have, therefore the input vector lies in the space Rk. And as for G, we have a mapping that maps this product to some other space, Rn, where n is the number of individual scalar outputs that we have, and all those things considered together is our output vector, which lives in space Rn. Okay, now from this, or for this nonlinear system, we will now obtain an approximation. And for this, let's begin from a very simple case and generalize. Now consider a function, let's call it f. It's a scalar valued function, and what it does is it takes values from R and maps to values from R, okay, from R to R. So it's the simplest kind of function. So okay, consider a function f from R to R, and suppose that function is smooth. Okay. That is differentiated without running into any trouble. Okay. Since it's from R to R, it's straightforward to draw it, but represented on the board. Suppose that it's something like this. Okay. That's R function. Z0, and this is our function f of c. Now, for some reason, let's say we're interested in this function at some, or behavior of this function, around some particular point in space, and let's call that fixed point z bar. Okay. Okay, so we are here. Some fixed point on the real line. Now, we're interested in the behavior of this function around that fixed point. So, to do that, what we do is we study its expression, f of c. But that expression could be quite complicated, and it may not be pleasant to work with. So, another way to go is, if you're only interested in the behavior of f in a small neighborhood of c bar, then we can work with f's approximation. Okay? And by approximation, we mean this line. Okay. That's the tangent line to the curve at point z bar. So this is our f of c, the actual function, actual curve, and this is called, which is a straight line passing through this point and tangent to our curve f of c. This is called first order approximation. At the particular point z bar. For another point, you will have another approximation because you will have another line. Now, around that particular point, we can express that line very easily. What we have is plus df over dz, okay? Slope of this line, that is df over dz, derivative of f evaluated at z equals z bar. Okay, so you obtain a number, a real number. In this case, it's positive, and then that times the deviation from the fixed point z bar. Okay, so this is the right hand side is the expression for the line. And clearly, if you look to the curve in a small neighborhood of z bar, now this line and that curve, they look very much like one another. Therefore, for many practical purposes, we can, instead of working with f of z, because it may be a difficult task, we can work with its first order approximation. We can work with that line. So this thing is called first order approximation of f around or at z bar. Now we're gonna take this nice tool of expressing a nonlinear curve by a line, and we're gonna generalize it to more general functions. Okay, and this is the idea. And this is what the idea is based on, basically. For values of z close to z bar, we can replace f of z with this approximation. Okay. And why we can do that is quite obvious to the eye, visually, because we're talking about a scalar function. Okay. Although it's not that obvious to the eye, still the idea is perfectly applicable to more general cases. Okay, so let's talk about that a little. This has a generalization to vector value functions. Okay, now let's see how. For this, let's begin again with a special case of the general case. That is, consider this time function f that's from R2 times R to R2, for instance, which may appear, for instance, as the right hand side of a second order system with a single input. Okay. Now this f, therefore, will look like this. It will be a vector. The first entry of that vector will be a function. Let's call it f of 1, and that will be a function of x and u. Now x is our vector in R2, therefore it will have two entries, x1 and x2. So let's write those entries explicitly. So what we're talking about is x1, x2, and u. So this first entry is a function of three variables, x1, x2, and u, three scalar variables. And similarly for the second entry, x1, x2, u. Okay, where this x is this vector x1, x2, or x1, x2 are entries of that vector x. Now the question is, what's the first order approximation, if there is one, of f of xu at some particular point in this space, R2 times R. At xu equals x bar u bar, some fixed point in R2 and some fixed point in R. Or together, you can consider them as a single vector, and we're talking about some fixed point in R3. Okay, so mimicking this thing here, that approximation, we can obtain the following approximation for f around this fixed point. But I will not be able to provide the usual demonstration of what's going on, because it's a bit difficult to draw. So f1 of x1, x2, u. So this function, which is the first entry of our vector valued function here, can be approximated at this point x bar, u bar, or x1 bar, x2 bar, u bar, as follows. f1, x1 bar, x2 bar, u bar. Okay. This is the value of f1 at that point where we're performing the linearization or approximation. Plus partial derivative of f1 with respect to the first variable, which is x1, evaluated at point x1 bar, x2 bar, u bar, okay, times x1 minus x1 bar, plus partial derivative of f1 with respect to x2 times x2 minus x2 bar, and finally the same thing for variable u. Okay, partial derivative with respect to u, and then multiplied by the deviation of the true u from the fixed u. Okay. And these partial derivatives are all evaluated at the point x bar u bar. X bar u bar. And x bar is x1 bar, x2 bar. Likewise, for the second entry, we have f2 of x1, x2 u equals, or approximately equals, f2 x1, x2 u bars plus f2 delta x1 times x1 minus x1 bar plus partial with respect to x2 times x2 minus x2 bar, and finally the f2 delta u times u minus u bar. This, combining those two approximations, allows us to write the approximation for the vector function f of xu. Therefore, we can say f of xu can be, or approximately equals, at least for values of xu that are sufficiently close to the point at which we're performing the linearization, the approximation. You can write this as f of x bar u bar plus. Okay, we can collect all those partial derivative terms and obtain a matrix. f1 delta x1, f1 x2, f2 x1, and partial f2, partial x2. Okay. Times vector x minus x bar, and plus partial f1, partial u, partial f2, partial u times u minus u bar. Okay. Here we have a square matrix. Here we have 2 by 1 matrix or a vector. Now this whole thing is called Jacobian, okay, partial of f, partial of x. Likewise, this is partial f, partial u. Now that these matrices, they are evaluated at this point, x bar, u bar. So they are actually real matrices, they are no longer functions, okay, they are constant matrices. So this is, therefore, the approximation of f at xu equals x bar u bar, or the first order approximation of f at this point, x bar u bar. Okay, now so far we have not introduced any dynamics to the picture. Okay, and from this point on we will continue with that. That is, we will consider this as the right-hand side of some nonlinear dynamical system, and then we will see what happens next. Okay, now return to nonlinear dynamics. Consider the system in state space representation. X equals f of xu, and the output equals some function of x and u, g of xu. Now the approximation of the right-hand side, namely the functions f and g, are as follows. Okay, we have f of xu approximately equals the value of f evaluated at the point of interest, which we're calling x bar u bar, plus this square matrix, partial of f with respect to x, evaluated at x equals x bar and u equals u bar, times this difference, x minus x bar. This is variable and this is fixed. And plus partial f, partial u, evaluated at, as before, x equals x bar and u equals u bar, times u minus u bar. Okay, so f of xu for points close to x bar u bar in space can be approximated, assuming that all the derivatives exist, can be approximated by this expression. Likewise, we can do the same thing for g. G x bar u bar. Basically, just replace all the f's here by g's. But let me do it anyway for the sake of completeness. G. U equals u bar times x minus x bar plus delta g delta u. U equals u bar times u minus u bar. Okay. Now, for ease of notation, we will give some names to the matrices that appear during the process of approximation. Okay. So let's call this A, this B, this matrix C, and that matrix D. So that we get closer to our linear system representation. Okay, so we let A be this matrix. Okay. It's a square matrix. B is this matrix evaluated at x equals x bar, u equals u bar. C equals evaluated at x equals x bar, u equals u bar. And finally, D is G u evaluated at x equals x bar and u equals u bar. Okay. They're all now constant real matrices because we evaluated these and then at some particular point in space x bar and u bar. So, with our new notation, we can write now the approximate dynamics of this system. Okay? So what x dot equals approximately and what y equals approximately around the point x bar u bar. Okay? So all we have to do is replace f and g by their approximations. In other words, what we can write is x dot equals f x bar u bar plus a times x minus x bar plus b times u minus u bar. And likewise, the output or measurement of the system should be close to this expression plus d u minus u bar. Now, given this approximation, now what we're going to do is we're going to introduce a further notation to help us see certain things a little bit easier in a way. Okay. To define psi as x minus x bar. So this is psi of t, it's a variable, it equals x of t minus fixed point in space x bar. So it's the deviation of the true state from the point where you're performing the approximation. And so this we can call as variation of state around state x around x bar. Okay. Likewise, define the new input, which is the difference between u and the fixed u bar, and define a new output, so to speak, w as y minus g of x bar u bar. Okay. Well, this thing you can also call y bar, because y bar is what you obtain when you plug in x bar and u bar to the function that generates y. Okay, now with our new notation, let's rewrite certain equations. Now, what we have is, or what we can write is psi dot. So by definition, it's d over dt, and definition of psi, which is x minus x bar. Now x is x of t, it's a variable, and x bar is fixed. Therefore, this derivative simply equals x dot, because this is fixed, x bar is fixed. Therefore, psi dot should equal x dot, okay? And therefore, since x dot approximately equals this, likewise, psi dot should approximately equal this right-hand side, okay? Now let's drop the approximately equal sign for a bit and use exact equality. Plus a psi plus bb. the W is C xi plus dV. Okay. Now, since we drop this approximately equal sign, what we're going to call this from now on is the approximate system. Okay. Now the question is, what's the relation of the approximate system to the actual system, the original system? Or what's the relation of the solution coming from the approximate system, psi t, to the solution x of t of the actual system? Okay. Now, solution of actual system is x of t, and the solution of approximate system is psi t. Now let's be careful or precise about what we mean by the solution. Okay, so what you do is you pick an initial condition and you pick an input x of 0 and u of t, and then you start the system from, let's say, t equals 0. And what you obtain is you obtain x of t. Now, for the approximate system, in order for us to be able to call this approximate system, we have to take the initial condition of xi 0 equals x0 minus x bar. Okay, so that's not an arbitrary initial condition, but directly defined by the initial condition of the original system. And likewise, the input of the approximate system must be such that whatever input you're applying to the original system minus this fixed vector, u bar. Okay, and same goes for the other. And then what you do is you obtain this exact solution, and then you obtain xi of t from your approximate system. And what's the relation of x of t to xi of t? Assuming that x and u remain close to x bar and u bar. In other words, this and that are small. They have small magnitudes. This is the relation. X of t approximately equals x bar fixed plus xi t. So that's the relation of the actual solution and the approximation. And y of t approximately equal g x bar u bar plus w of t. And this approximation should be good in some sense, provided that x and u remain close to x bar and u bar. Okay? As long as x of t, u of t remain close to x bar, u bar. Okay. Now, here comes the question. Taking or concentrating on this system, we can ask a question. And the question is, when is that system linear? When is the approximate system linear? That is, when is the linear system? Okay. The answer is, well, we know how a linear system looks like. It equals let's call the state z that equals az plus b times the input. Okay. Now this looks like, and y equals cx plus du. Now this looks like almost looks like our linear system definition. We have a nice a times the state term, we have nice b times input term, but we have also an additional term. This is the unwanted term because it doesn't appear in our linear system definition. Therefore, the answer to our question must be that when this term here is 0, so that we can just erase it, and we have the state space representation of an LTI system. Here is the answer. When f of x bar u bar equals the zero vector. Because when f of x bar u bar equals 0, we have xi dot equals axi plus bb, and w equals cxi plus db. Okay. This is called the linearization of nonlinear system. X dot equals f of xu, y equals g of xu. Statement is not over, and the last part is very important. This is called the linearization of nonlinear system at the equilibrium point x bar u bar. Okay, so if you, and the definition of equilibrium point is this. So if you obtain an approximation of the nonlinear system at a point that's not an equilibrium, then what you obtain is not a linear system. Okay, so it's a linear system only if you're doing your approximation at an equilibrium point. So let's emphasize that fact by giving the formal definition of an equilibrium point. Here's the definition. For a system, x dot equals f of xu. Equilibrium has nothing to do with the output part of the state space representation. It only depends on the dynamic part. An equilibrium point x bar u bar is any real solution to this equation. Okay, f of x bar u bar equals 0.